All right, so welcome to We Know Way Too Many Things right now. Here right now, lecture series. We're starting off with Benjamin Summers and myself, Charles Dunn. And yeah, hopefully you guys will learn something outside of your field, and we'll manage to not make our field completely ridiculous. Yeah, all right, Benjamin Summers.
Completely ridiculous.
Yeah! So first off, as you might have seen, I am the least successful structural engineer from the introductory structural engineering class. Our bridge failed at 1/12 the capacity we expected, precisely because we hadn't taken what I'm about to show you today and didn't understand what the hell was going on. We wound up filming it and still couldn't explain what happened. You would have been able to explain that in the next 15 minutes. All right, so we're just going to do this really quickly. You have a beam, right? There's two kinds of forces that can act on a beam. One's called just a force. That's pretty clear, right? It's something pushing on it. Generally, when we're talking about bridges and anything static, that force there's a reaction force that is equal and opposite, so all the forces sum to zero. If that's not true, the thing moves. The other kind of force that will act on something is a little less intuitive. It's called a bending moment. This involves, the idea is, if you imagine this is the beam, right? A force would be pushing in the plane of it. If you imagine you attached a long rod here and then twisted the rod, it's like putting a torque on it. So a bending moment on this beam would cause it to do that. Or like a bending moment like this would cause it to do that. And you can actually put a bending moment on beams. And it's very easy to talk about this as bending moment versus shear. That's sort of what we talk about. Now a beam is going to break in one of two ways, and we'll talk about what they are. But let's see, where do we start? Right, so we're going to take an imaginary beam. And on this beam, we'll take two imaginary beams, and we'll apply two kinds of forces to them. Here, we'll apply one concentrated point load in the middle, right? So this is just like one point right in the middle, right there. And the question is, what are you going to get? What are you going to get inside the beam? What's it going to feel? And we're going to go back to these two concepts of sort of force and moment. And inside the beam, you'll see that there's going to be a constant force here, and it's going to do that, and it's going to like that for the moment. So the point is, right here, the beam is going to feel one force. Just ignore the rest of the beam, right? So there's going to be a constant force like that. And the rest of the beam is going to be pushing down at the same amount. So inside, there's going to be a force trying to get all the little particles in the beam to go up or down. And we call this shear. It's like shearing off, right? And that's one way that a beam can break, is you just push on it too darn much, and the particles just break in the same direction that you push on it. The other way it can break is because of the bending moment. And that's a little bit more complex, and that's actually how our bridge broke. And that's how a lot of things break. So we'll talk about that in the lecture. And the whole point of this class is to talk about, this 15-minute talk, is to talk about where things are going to break. All right, so we'll talk about a beam. No, first we're going to talk about a spring. It's the one other physical concept we're going to have, which is when you take a spring and you stretch it, right, there is some resistive force, and that force is proportional to how much you stretch it. And the thing that's proportional to, we call it K, it's the elastic constant. In structural engineering, you use E, it's called Young's modulus. It's just a spring constant. The difference is it's really, really, really large, and it's per area. But so for steel, it's like 29,000 kips per square inch. So 1 square inch of steel, if you strain it, will produce 29,000 pounds of resistance. It's really strong. Okay, so let's talk about a beam. What happens to a beam? And this beam can be anything. It can be the roof above us, this beam right here. It could be, maybe more useful is your bookshelf. You want to load up your bookshelf and figure out how it's going to break. So you take your damn bookshelf, and it's right here, and we start putting weight on it, right? What happens when you start putting a ton of weight on something?
Falls.
Falls, that's one thing. If you resist it, it starts to bend, right, as well, especially if it's a little bit. So you start to get something that looks a little bit like this.
Then what are the bottom two areas?
Sorry. Appreciate that. So that's a force, and that's force. All the arrows just represent forces. And what you're going to expect is the beam is going to actually start deflecting out like that. It's going to start to bend like that. And what you'll see, the interesting thing, is the part up here actually winds up being in compression. So if you can kind of imagine that, you can show it mathematically. I'm not going to bother, but the top right here, as you bend a beam, winds up pushing in against itself. So the more you push, the more it pushes out. The part in here actually winds up being stretched, right? So the more that you stretch it out, the more that it pulls back in. And actually what you wind up finding is the further you move away from the middle of the beam, this is just the little middle of the beam, this is actually not stressed at all. The little bit here and the little bit here, the further you move away, the more it gets stressed, linear with how far you go. So the place where there's going to be the most compression is going to be right here. The place where there's going to be the most tension is right here. If we go back, remember that shear thing? There's two things, there's the bending moment and the shear. So this is bending moment, and the most stress from bending moment is going to be here. The most amount of shear strength, right, the part that's causing it to go like this, is going to be found actually right here. Especially, let's go back to your bookshelf. Your bookshelf looks a little different. You're loading it here, and here, and here, and here with all tons of books, right? And that's resisted right here. Well, it turns out these forces are really big. So you're putting this whole big force right here, which means that you're gonna get a lot of shear right there. So why does that matter? You get a lot of bending moment right here, and actually the part that gets stressed the most, that gets like pulled apart the most, is the part right here. The part that gets compressed the most is the part right here. And you also have shear, and shear is the greatest right towards the edge right here. Reason that matters is, let's say you're inspecting something, and you wanted to figure out where it's going to break. You like have your new bookshelf, and you've loaded it up with books, and you want to know if you can add one more thing. And you look at your bookshelf, and it's starting to deflect a little bit. The question becomes, where would you look for cracks? Where is the thing going to start breaking? And there are two places. And I'm praying to God one of you is going to have an answer for that. Well, besides John and Eric, sitting next to you right now because you take these already. There's like two places you can look for cracks. Any guesses? Where are the most forces? Yeah.
The middle, the bottom.
Right, exactly. The middle at the bottom, and there's one other.
The left.
Which is right, actually, at the left. And if you look at any structure and you're worried, is it okay? That's exactly what you're looking for. Is it going to shear? And if this were to break up here, the way it would break is it would actually just go like that, and it would just fall. The way it would break right here is a little bit weirder, because it starts to do
Like snap apart.
It would kind of snap apart, right? So the question becomes, given that this is in tension and this is in compression, how do you want to build your beam, right? We're gonna look at the cross section. Let's say you have a bunch of concrete and you're trying to build like a big new building. The way you build a reinforced concrete beam is built directly off this. Concrete's like this material, and concrete does really well in compression. The moment you start straining it, it's pretty much useless. You actually assume that it has some small, like 0.15 of the tensile strength, that's compressive strength. So what you do is you put steel in it, and that's the whole reinforced concrete. It's like, well, I'm gonna be bending my concrete beam like this. If I just had concrete, it would fail right there because of the bending moment. If you put it into tension, everything would come apart. So what I'm gonna do is I'm gonna take steel and I'm gonna embed the steel in the concrete. Where do you embed the concrete? Where do you embed? So I'm gonna take the concrete and embed the steel. Where do you put the steel in the beam for it to have the most effect? That's the question. Any guesses?
Under it.
What?
Under it?
Under it, yeah, absolutely. Where it's going to be strained. And actually, where it's going to be the most strained is right at the bottom. So you'll see in a normal concrete beam, you'll see all the reinforced steel sits right at the bottom. And that's what's taking all the tensile. Cool. That's it.